All right, so let us now review our proof of concept demo and show you all the pieces. And for those of you who are engineers and technically inclined, certainly be very welcome to follow along. What we have right here is just a cantilever stainless steel beam that has 8, as I mentioned, standard micro S1 Intellivibe transducers on it. 4 on the top surface and 4 on the bottom surface. Those sensors, as I mentioned before, do not take any input power. They produce their own signal without any excitation or power. And that signal is then driven into some electronics that do their magic, as well as the communication module. And the result is shown on the computer screen. The speaker here which just plays the role of a simple shaker, is driven by a simple audio amplifier. There's absolutely nothing too complicated about that. And if we glance on the floor below, we see a little household, standard household type grinder that will provide a bit of excitation to the floor here. And just to mention that this is an industrial building and the floor is a full concrete floor. So just when you try to kind of imagine in your mind the level of vibration and how it goes through this floor, please keep in mind that this is an industrial building here. And beyond that, there's not that much to show in terms of our setup. Again, transducer, conditioning electronics, and communications, and a further excitation unit for the floor. Let us now go to the meat of our demonstration here, and we'll go through a number of use case scenarios. But before we do that, let me guide you through the screen so everybody understands what's happening here. So this display shows us the excitation signal that is sent to that speaker shaker and basically simulates a rotating equipment. This signal is a sine, but as it happens, it's a low frequency sine that gets truncated by the speaker itself and creates a kind of a truncated sound that, at least to our ears, sounds very much like an internal combustion engine. This screen here shows us the sensor signal from which all the fault detection is done. And then we perform 2 frequency type analyses on that signal. The one is a high frequency side and the other one is a low frequency side. And in addition to that, we have some other buttons and controls. This control allows us to simulate a kind of a low frequency fault, something like a rattle or let's say a situation where the cooling fan is encountering some sort of an obstruction, or those types of faults. And then this control here allows us to simulate a high frequency fault, which is more akin to a loose drive belt or maybe a faulty bearing that creates a high frequency squeal. And we're all familiar with those situations that happen in internal combustion engines. Let us now simulate a low frequency type fault, which actually means that something is happening to our engine that is of a low frequency nature, such as maybe an obstruction in the cooling fan or some sort of banging, clunking, and that type of event. So let me introduce this type of sound. And what we see here is that the monitoring block, and by the way, I just got a message on my cell phone that fault was detected. What we see here is that the monitoring block detected fault, and that's indicated by this light becoming red. And then the analysis block performed analysis and basically concurred with the monitoring block that in fact there was a fault or a departure from normal. And what we see here is that the kind of departure we get is a general fault. In other words, it's just more loud. It's more loud generally, and it's more loud in the low frequency spectrum as well as in the high frequency spectrum. The one thing that we are not detecting is just a distribution into high frequency without a general increase in the vibration amplitude. And that's what we would expect here to see. So if a fault of that nature or indication of that nature is sent to a user, the user will know to expect more of a clunking, banging type noise and not a squeal type noise from the equipment. And that's something that can lead us to make also some smart decisions about how quickly we should make our way to the equipment and the level of emergency that this fault detection entails. And of course, for others such as security type applications, this also has its own uses in terms of separating between high and low frequency. Let us now review the next part of this proof of concept demonstration. And this part will talk about detecting ground vibration for many possible security type applications. And just to review, I'm standing in an industrial building on a concrete floor. And then on this floor, we have a standard lightweight laboratory bench. On top of the bench, we have a speaker, which is basically a spring suspension. And on top of the speaker, we have our sensor. We have our system running in acquisition mode. So there is no excitation provided by the speaker. The speaker is off. And what we're going to detect now is basically me lightly tapping my foot on this concrete floor, a distance, diagonal distance of probably 1.5 meters from the sensor or so. But again, you can imagine this vibration going through all the steps that I just mentioned. So let's just give it a whirl. Oh, and just got a message telling me that fault was detected. And as if you switch your attention back to the screen for a second, you will see that the monitoring block issued an alert, which is indicated by the red light. And then a general fault was issued, meaning that the general level of vibration was exceeding normal levels. And this was based on a fairly soft tap of my foot on this concrete floor here. Now again, I should mention that this proof of concept hasn't been optimized for any particular application, for example, detecting ground vibrations. It is rather, it was designed, generally speaking, to showcase and prove the concept of the technology. So if there are customers who are interested in specific applications, certainly this will need to be customized for those different applications in terms of the software content, the detection thresholds, and so on. At this point, we will do our final demonstration. The system is running in acquisition mode. The shaker is off. Everything else is the same. And the only thing I'm going to do now is turn off this grinder. All right, so grinder was turned on. The system detected fault. And sure enough, as I was turning the grinder off, my phone sent me a message that alarm was detected. Switching our attention again to the screen, we see the same situation as happened before when I tapped my foot on the floor. The monitoring block has detected fault. The fault type was general fault, indicating a general increased level of vibration. And the SMS light, the user alert light, has also been turned on. And in fact, the user alert message was received by the registered user, in this case, myself. So to briefly summarize, what we have shown here is the capability of our transducer, which is a very simple, inexpensive, robust transducer, to detect a variety of vibration events based on knowing the the normal vibratory signature of this environment, of this room, of this floor, of the speaker and everything else. And what we were able to demonstrate that a departure from this normal environment was able to be detected and classified, at least in the low frequency, high frequency sense, general fault versus only high frequency fault. And the detection was triggered by a simulated environment, which is a shaker, and a more real environment, which is a floor excitation using an impact type event, me stomping on the floor, and the more continuous excitation type event, which is the little grinder that we used here. Now that we have been through the proof of concept demonstration, let us summarize what we have seen here. Under development is a truly paradigm-shifting vibration detection and classification platform that has a large plurality of civilian, homeland security, and military applications. The product platform relies exclusively on the Intellivibe transducing platform that is protected by 5 issued patents and is already in use by leading companies in the semiconductor capital equipment space. The R&D was supported by federal and provincial governments of Canada and Nova Scotia respectively, and that is something that we are very proud of since it's a very validating event for our technology. And the product rollout for early adopters is expected by the end of the 4th quarter of this year, 2013. We do actively solicit other users' ideas and requirements so that we can learn from our potential user base. And we are also in contacts with a number of potential early adopters, and certainly would be willing and excited to hear from other potential early adopters and users, and our contact information will be provided. So first of all, we would like to thank the Nova Scotia Community College and especially Drs. Sendamour, Joseph, and Mfumu for their generous support and the use of lab facilities. We would also like to thank the National Research Council of Canada and our industry technical advisor, Mr. Gary Bustin, for his belief in our technology and unwavering guidance. Thank you, Gary. Mr. Chris Lodeman of Turbulent Research and Mr. Joe Hood of Acoustics provided some invaluable input into the hardware design and software design of the product, respectively. The Government of Nova Scotia provided generous support via the Innovation and Productivity Voucher Program. And finally, Mr. Mike Morris of Seaforth Energy provided us with very valuable business intelligence and advice. Thank you very much for your attention, and we hope to hear from you.